Today we're going to be looking at graphing absolute value functions. Absolute value is probably a concept you're familiar with, and you might remember from the past things like this. Square root of -3, for example, is equal to 3. And at the same time, square root of +3 is equal to 3. And it's because of that we have two different values that can give us the same result, since absolute value gives us the positive answer. And what happens in our graphs is what we're going to expect is to see a graph that has repeat values. Now we've seen a graph that does that already, a parabola, but in this case with absolute value, we're going to attribute the shape of the graph to a very sharp turn V. So we're going to have a sharp corner down here instead of the slow curve of a parabola. And this would be a case of absolute value opening upward at the same time. We could have this V opening downward as well. So those are the two shapes that we're looking for. And that's what we should see happen in every absolute value graph. So let's take a look at a few things here to help us out in making these graphs. So as you look at the graph, you might notice that there is this turning point, and that turning point we call the vertex. And we practice looking at vertex form with parabolas. And to do that, we looked at the equation of a parabola. And in this case, we're going to look at the equation of the absolute value function in vertex form, and where we have x plus something or minus something inside the absolute value bars, and then we'll add or subtract some value at the end. And these two numbers tell us how the graph shifts. So right here you can see that description. You see that h is a horizontal shift, left or right. So if we have a number inside the absolute value with x, that is going to cause our vertex to either move to the left or to the right. And similarly with k at the end of the equation, if it's a positive value, we'll move up, and if it's a negative value, we will move down, just like we saw with quadratic functions in the past. And if we can identify the directions that the graph has moved, even if one of these values is 0, we'll know where the turning point is going to be, which then helps us get to making our graph a little more efficiently. So all we'll do is we'll identify that vertex as best we can, and then we'll graph using a calculator, and we'll create a table to plot our graph on the grid. And we'll make sure we have that nice V shape to this. So let's look at example 1. We have f of x equals the absolute value of x minus 2 and minus 1. So first thing to recognize is inside here we have a value being subtracted with x. Now that is our h value, and the value at the end would be referring to k. Now, if you remember from h, the way this one works is a little bit opposite of what our brain would think. We know h moves us left or right, and it's the opposite of what we tend to think here. If we see a minus 2 inside, that's going to mean to the right 2. So the horizontal shift is going to move us to the right 2. So that one works the opposite of how we would interpret it typically, but the k value is very direct. If it's a minus 1, it moves in the negative direction downward. If it's a plus 1, it would move us upward. So because we have a minus 1, we know that we have a shift downward by 1. So if you think about what these two things mean, all you have to do is start at 0, 0, go to the right 2 units and up 1 unit, and now we know where the vertex is located. So our vertex is going to be at positive 2, negative 1. Okay, and it's very helpful to find that vertex because we could kind of view that as the middle of our graph. It's where the two halves of our V are going to stem out. And if that's the case, if it's the middle of what we'll be graphing, then we're going to put that vertex in the middle of our table. That way we show each half of the graph on either side. And as far as making these graphs, we don't need to overwork ourselves here. We can just count by, I like to put lower numbers on the top, count by ones in either direction. So we'll put the lower numbers there, the higher numbers here. It doesn't matter. Just very standard to have your lowest numbers at the top of the table, but we could reverse that if we want. Okay, now as far as making this table, we could do this by hand if we want to substitute these x values in and evaluate, or we can use the graphing calculator to help us out too. So if we open a calculator such as Desmos and type in our equation, And you can leave it as function notation, f of x equals, and we have the absolute value of x minus 2. Now you can use your keyboard. You can also use the vertical bar located above the enter key on your keyboard as well. So I'm going to have the expression x minus 2 inside our absolute value. And we see that V shape showing up. I'm going to close my absolute value bars, and I have a minus 1 afterwards. And I just realized that I put the vertex in the wrong location. I went to the right 2 and up 1. So let's go back here and change that really quickly. Go to the right 2 and down 1. There we go. Okay, so now we're at 2, negative 1. And that's exactly what we see on this graph. Notice it's putting a nice point right there. Okay, and so from here, we want to talk about how do we make the other ends of this graph. So let's try that out. Let's create a table. And you notice the table always has the default values going from -2 to +2. And for my table, I have it going from -1 to +5. So I'll start at -1 here, then go to 0, and I'm just going to type in all the values I had in my table. And there we have it. Now, something we should be seeing is if we're putting the vertex in the center of our table, we should see repeating values on either side of that vertex. Because what's happening at that vertex, remember, is that the graph increases at the same rate on either side. And so we should see this increase to the right at the same rate as we go to the left. So we're going to have repeating values on either end. So these dots are at the same heights. So let's go ahead and copy those into our table. So we have 2, 1, 0, and 0, 1, 2. And all we'll do is we'll plot those points on either side. And make that very sharp V shape. So if I pull up my drawing tool here, I should be able to do that pretty well. Okay. So that V shape here, let's make it the same color. It's going to start at my vertex, extend in this direction, and same thing on this side. Start my vertex and extend in this direction. And we could continue those points onward, but we've shown the shape of the graph. We've shown how the V is going to move. And there we go. There is our absolute value function. We could show some things for later. Here's our vertex, for example. And that's all there is to these. So an absolute value function we could actually think of as two separate linear functions where we have a ray going in this direction and a separate ray going in that direction. Okay, so let's give this a try. Again, down here with another example, we see the function f of x equals -2 times the absolute value of x plus 3. Okay, so let's walk this through again. Here's h inside our absolute value bars, and you notice there is no k present at the end. Okay, so let's think about what that's going to mean for us. First off, starting with h, that plus 3 is either going to move us to the left or to the right. And remember, this value does the opposite of how our intuition would tell us to interpret it. So if we see a plus 3 inside, that is going to mean to shift to the left 3. So h goes in that opposite direction. We see a plus 3, that's going to take us to the left. But whatever k is, it's very direct. If it's plus, it goes up. If it's minus, it goes down. But in this case, we have no k. And we have a missing value here because k would have been plus 0. So as far as a vertical shift, there isn't one. Maybe we just say it's 0 or none. However, 0 is a good number to think about when we say none, because we want to talk about where this vertex is. And if we started our origin 0, 0, go to the left 3, and then stay there, we do not shift up or down, we would be at -3, 0. And there's where that 0 came from. So negative 3, 0 is our vertex. We're going to create our graph. So let's fill in some values. First integer lower than negative 3 is negative 4, so I'll count by ones going this way. And I'll count by ones going in the other direction as well. Okay, so let's try this one out. Going back to our calculator here, typing in our new equation. Okay, so we have negative 2 times the absolute value of x plus 3. Oops. Okay, close our absolute value bars, and there we go. There's our vertex, just like we said, at negative 3, 0. So that's handy. All right, so we need some more points ranging from x values of negative 6 to 0 to complete our table. So starting at negative 6, here's our table now. It is altered with us. Seems like a new feature on Desmos now where they make the table in a separate line. That's handy. Let's change these values to what we wanted. So the top of my table had a negative 6. So I'll start there, and I'll work my way down to 0. So negative 6 to negative 5, negative 4, negative 3, negative 2, negative 1, and 0. And here's our test again. Our vertex supposedly is in the middle, and when we look at it, we have repeating values on either side. Perfect. Okay, so here's negative 3, 0. Let's fill in our table. At negative 6, I had negative 6. Negative 5 was at negative 4. I believe negative 4 is at negative 2. Okay. And we had negative 2, negative 4, and 6, these repeating values. So very simply here, we can plot these points, negative 4, negative 2, and negative 5, negative 4, and negative 6, negative 6, negative 2, negative 2, negative 1, negative 4, and 0, negative 6. Okay. So based on this, we have that V shape again, and all I need to do is draw those rays coming off of the vertex here. So start here and draw through. And I like to start the vertex and draw in this direction as well. Put some arrows on the end, and we should have it. Okay, so here's our vertex. All right, and that's really all there is to plotting a graph of an absolute value function. Now, before we end here, just one last observation that might really help us out with our interpretations of what is going to happen ahead of time. You might notice in this graph in particular, the spacing between each point. So if we look here, you notice if I start the vertex and move this way, to get from 0 to negative 2, I just need to subtract 2. And if to get from negative 2 to negative 4, I subtract 2 again. To get from negative 4 to negative 6, I subtract 2 here. And you notice that's going to happen on the other side too because we have repeating values. Let's go ahead and use a different color for that. So let me get rid of those last markings I had so we can see it a little bit better. It's not all blending together. This purple arrow is going in a different direction than the green arrow. However, we're having the same effect on either side of this vertex. So what is that telling us? That's telling us the rate of change between our y values is consistent. It's constant. It's not changing. And that is a attribute of a linear function, right? Where we have a slope that never changes as we draw a line. So if we think about starting at the vertex and analyzing in either direction, we also have this idea of kind of a slope here. Now, where does that come from? Why is it a negative 2 instead of negative 7? Well, it's all based on your equation. If you go back to your equation, we have a negative 2 in the beginning. And that could kind of be viewed as our slope when we start at the vertex. I'm not going to call it slope because that's a term that we coined with a linear function, but it works the same way. If you start at your vertex, it's kind of like you have a couple of parts of a line coming off of it. So starting at your vertex, if you use this -2, we could just start at this point and show the following points because we know each one is going to be 2 below it. And if we're going to create this V shape, we just need to go down 2 and over to the 1 in either direction. And then you do it again. You go down 2 and over 1, down 2 and over 1, and down 2 over 1, and down 2 over 1, to where we just keep spreading further apart, making this V shape. So it's kind of like we had a slope of -2. And we could do the same thing here. If you notice these points, something similar, the spacing, to get from -1 to 0, we would add 1. To get from 0 to 1, we add 1. And to get from 1 to 2, we add 1. And it's the same going in the other direction since these values repeat. It goes up 1, and up 1 again. Same reason as before, should be. And if you go back to your equation, you notice at the beginning, we don't see a coefficient in front of our absolute value, and we know that the understood coefficient is always 1. And if 1 is our coefficient, then we can think of that as our slope. And again, I don't want to call this slope exactly, but we could use it that way if we started our vertex, to where if you identify the vertex at 2, -1, then all we have to do from there is use that, what we'll call slope, and go up 1 over 1 in either direction to create this V shape. And then we'll just continue the trend, up 1 over 1, up 1 over 1. Same in the other direction, up 1 over, up 1 and over. And that's just a very quick way to get an analysis of what these graphs are going to do when they're written in this format, because we can look at the equations, we can see where the vertex will be located based on the values, and then we can use this idea of slope to have an idea of what it's going to do, whether it's going to be a positive slope that opens the graph upward or a negative slope that causes our graph to open downward. So see if you can use that to get an idea of what this graph is going to do before you type it into that calculator, and hopefully the calculator confirms what you were thinking.